Hello. Today we will talk about one of the very prominent secondary structural elements in protein is alpha helix. Along with beta sheets, alpha helix are found as a secondary structural element in protein structures, and is almost 60% on average amino acids in a protein. They are present in form of secondary structural elements. So alpha helix was first predicted by Linus Pauling in 1951 from California Institute of Technology, USA. And what Linus Pauling thought is to have a chain of amino acid, a polypeptide chain, in as much as possible in extended conformation, and at the same time to maximize number of hydrogen bonds between peptide groups Cu and NH in that polypeptide chain. What was actually experimentally validated in 1962 by John Kendrew, when the first protein crystal structure was determined for myoglobin. So this Linus Pauling predicted that this sequence of polypeptide, when you have maximum number of hydrogen bond and you are keeping chain into possible extended conformation, that resulted into a helical structure that was termed the name alpha helix. This alpha helix is right-handed in nature. Right-handed means if you look at the helix, and helix is going away from you, and the path followed is clockwise, means if you have something like this and you move it, a spring like this is going away from the viewer in clockwise manner. For example, say viewer is on the downside, and if you move it like this in a clockwise direction, this is called right-handed helical structure, right-handed helix. Similarly, if you have helix is moving into anti-clockwise direction, so in that case this is called left-handed. So there are two forms of a helix can be found, right-handed and left-handed. In case of protein structures, because amino acids are in L isomeric form, so L amino acids, they always form right-handed alpha helix. These two alpha helices are non-superimposable mirror images of each other. So right-handed is mostly found in case of protein structures. For amino acids to acquire alpha helical conformation, the torsion angle phi and psi should be -60 and -50 respectively. It means that if you look at the phi psi map, what is also called Ramachandran plot, alpha helical conformation will be phi and psi -60 and -50 somewhere here. So this is the area where alpha helical conformation lies in Ramachandran plot. So these phi and psi torsion angles are required to bend polypeptide chain into alpha helical conformation. When amino acid is present in completely extended conformation, the length of an amino acid is 3.8 angstrom. But when this amino acid is present in alpha helical conformation, when it has to be part of the alpha helix, the rise per amino acid, the length of amino acid, the effective length of amino acid adding to alpha helical conformation is 1.5 angstrom. It means one amino acid will have 1.5 and will give 1.5 angstrom length to the alpha helix. There are on average 3.6 residues per turn of alpha helix, and per turn there are 14 atoms. That's why sometimes alpha helix is also called as 3.614 helix, because per turn you have 3.6 residues. Residues means amino acids where when amino acid is present in polypeptide form, water is removed. As a result, it's called residues, amino acid residues. So there are 3.6 residues per turn and 14 atoms. And the pitch of alpha helix is 5.4 angstrom. Pitch means the length of one turn. This is one turn, for example, and this is 5.4 angstrom. So every turn will have a length. The rise of turn, length of the turn is 5.4 angstrom in alpha helix. Another very important feature, property of alpha helix is hydrogen bonding pattern. All the secondary structural elements, they are stabilized by hydrogen bonds only. So in case of alpha helix, the hydrogen bonding pattern is N plus 4. It means first amino acid will form hydrogen bond with plus 4. It means the fifth amino acid. For example, carbonyl oxygen of peptide bond of first amino acid or any amino acid will be linked to amido group, NH group of peptide bond of fifth amino acid, N plus 4, fifth amino acid, NH group. Similarly, NH group of first amino acid will have a hydrogen bond with the fourth amino acid, carbonyl group of the fourth amino acid in reverse direction. The radius of the helix is 2.3 angstrom. Alpha helix is a cylinder, so the volume of alpha helix can be calculated using formula pi r square h, where r is the radius, which is 2.3 angstrom in case of alpha helix, and h is the height of the helix. For example, if you have 100 amino acid long alpha helix, so we need to in order to calculate volume of the 100 amino acid long alpha helix, amino acids is 100. So what will be height of the alpha helix that we need to calculate? Then we can put into the formula. For example, we know when you have 100 amino acid present in alpha helical conformation, the length of one amino acid contributing to the cylinder, contributing to the alpha helix is 1.5 angstrom. That's called rise per amino acid. So it means one amino acid will have 1.5 angstrom effective length. So 100 amino acid would have H is equal to 1.5 into 100 angstrom. So that's how height can be calculated. When you have height, you can simply put into the formula in order to calculate volume of the alpha helix. Okay, let's talk about hydrogen bonding. Hydrogen bonding is one of the main feature of alpha helical structure. So the pattern of hydrogen bonding is N plus 4. It means any one amino acid involved in alpha helical conformation will form hydrogen bond with plus 4, means fifth amino acid. If you talk about carbonyl group, for example, look at here, this is some amino acid, say number 1, carbonyl group CO, peptide bond facing up, NH going down. We know that peptide bond is present in trans configuration. It means CO and NH, they are oriented in opposite directions. So CO, for example, here facing up, NH facing down. This is N2C terminal sequence of alpha helix. So this CO group will form hydrogen bond with plus 4, means fifth amino acid, NH group of fifth amino acid. Similarly, this NH group of first amino acid would form hydrogen bond with, in this direction, in negative direction, carbonyl oxygen of some amino acid. But because this is first amino acid here, so there is no chain exists beyond this first amino acid, so NH group will be free here. NH group of first amino acid will be free because there is no partner available. Only carbonyl group will be forming interaction with NH of the fifth amino acid, and so on. And because the pattern is N plus 4, it means first 4 amino acid will have 4 NH group free because there is no sequence present beyond the first amino acid. Only CO group will be engaged in hydrogen bonding in alpha helix. Similarly, if you talk about the C terminal side, NH group of last fourth will be engaged in hydrogen bonding, and CO group of last 4 amino acid would be free. It means if you want to count number of hydrogen bond in an alpha helical conformation in an alpha helix, you need to consider these vacant positions, the vacant atoms from C terminal side and N terminal side. Because bonding is N plus 4, it means 4 amino acid will have NH group free here and 4 CO group free here. So that means 8 atoms or 4 hydrogen bond would be missing from total number of hydrogen bond present in an alpha helix. Now let's take an example for calculation of number of hydrogen bond in an alpha helix. Say you have an alpha helix with 100 amino acid. It's a 100 amino acid long alpha helix. How many number of hydrogen bonds would be present in that alpha helix? So 100 amino acids means you will have 100 CO group and 100 NH groups. And if you allow them to pair in order to form hydrogen bond, there would be 100 pairs. 100 pairs of hydrogen bond. It means there are 100 hydrogen bonds, 100 pair of atoms involved in hydrogen bonding. So there will be total 100 hydrogen bonds. So, but we know that in alpha helical conformation, 4 NH group are free from N terminal and 4 CO group are free from C terminal, which are unpaired, which have no partner to form hydrogen bond. It means 4 plus 4, 8 atoms are free. They are not making any hydrogen bond. 8 atoms means 4 pair. So 4 pair, the total number of hydrogen bond would be 100 minus 4 is equal to 96. So it means in an alpha helix of 100 amino acid length, 100 amino acid number, the total number of hydrogen bond would be 96 because 4 are used. Similarly, if you talk about some other helix like 310 helix, we'll see later. In that case, there are three atoms free this terminal and 3 at this terminal. So it means in that case the number will be 97. In alpha helix, every amino acid is present at 100 degree to the previous one. It means, for example, if you have the first amino acid located at 0 degree, so second amino acid would be at 100 degree, third would be at 200 degree, then 300 degree, and so on. So it means if you keep adding, for example, first amino acid is at 0 degree, second would be at 100, because every consecutive amino acid is present at 100 degree of the previous one. So if first one is at 0 degree angle, second amino acid will be at 100 degree, third would be at 100 plus, keep adding 100, 200, fourth would be at 300, fifth would be at 40 degree, means fourth is at 300, so fifth will be at 40 degree because 360, it completes at 360, third will complete at 360 degree, so the fifth amino acid will be at 40 degree, sixth will be, keep adding 100 again, so 140, and so on. So you require 18th amino acid. The 18th amino acid would come again at 0 degree. It means if you have 18 amino acid, the first amino acid will superimpose exactly on the 18th amino acid in alpha helical conformation. If you look at alpha helix from the above, from the top view, if you look at the top view, you will see a circular structure like a spring. You are looking at the upper side, looking from the top. So in that case, the first residue in alpha helix would exactly superimpose on 18th residue. If you look at the alpha helix from top side, if you look at the top view, you see a circular structure like if you have a spring and you look at the spring or a cylinder from the top, from the above, you see the spherical thing. This circular thing is called helical wheel, alpha helical wheel, and we see that in alpha helix all the side chain of amino acid, they are protruded outside. So they do not theoretically interfere in helix formation because they are not involved in any interaction. In alpha helix, hydrogen bonding interaction occurs only between peptide bonds, the main chain CO and NH groups. Side chain are free to accommodate themselves in extended conformation. So theoretically they do not interfere with each other and helix formation. But in case of say polyglue helix means if all the amino acids in alpha helical conformation are glutamic acid or aspartic acid. So in that case, if you keep that helix at different pH value, helix structure get interrupted and the helix turn into coil structure. Disruption of helix is called into coil structure is called Helix-coil transition. So for example, in case of polyglue helix, if you keep at pH 2.0 or 7.0 or say 10.0, the stability of polyglue helix would be different, because if these side chains, all side chains are negatively charged, there is a repulsive force exists between these side chains, they will repel each other, they will push them apart. As a result, this helical structure is disrupted and helix turn into coil structure. So we have to look in case of polyglue helix at different pH values where these side chains are charged. In case of polyglue helix, the pK value of side group carboxyl group is around 4.3. So it means up to 4.3 pH, the carboxylic group of the glutamic acid side chain will be in COH form, neutral. There is no charge up to 4.3. At 4.3 is a equal charge. That's why it's a pK of side chain is 4.3. But if you go above 4.3, the predominant species in side chain of glutamic acid is carboxylate group. So it becomes in COO minus form above pH 4.3. It means if you keep a polyglue helix at pH more than 4.3, all the side chains will be negatively charged. As a result of this negative charge, this negative repulsion will cause helix to disrupt and to turn into coil. So if you talk about different pH value, the polyglue helix will be most stable at pH 2, because as pH 2, side chain of glutamic acid in the helix will be all in protonated form. As a result, there will not be any charge. The neutral, it will form in it will have exist in neutral form. So when there is no charge in side chain, there is no repulsive force. As a result, helix is more stable. Similarly, if you keep going pH up, if you keep increasing pH, stability decreases. At 10 pH is the maximum here. So it means at 10 is totally disrupted. 10 there is no alpha helical conformation exists in case of polyglue helix. Similarly, you can think about a polylysine helix also. The logic will be same. If you have polylysine helix, means all the side chains are lysine amino group, and the pK value of lysine is say I think around 10.6. So it means up to 10.6 pH, the lysine side chain will have positive charge, because amino group, if you keep at low pH, we know the rule. If you have pH lower than pK value, there is a protonation. If you increase pH more than pK value, there is a deprotonation. So lysine side chain is amino group, pK value is 10.6. It means less than 10.6 pH. If you keep polylysine helix, side chain will have positive charge. So these positive charge again will cause repulsion, positive repulsion. As a result, helix structure is disrupted, and there is a transition occurs from helix to coil at pH less than 10. So in order to stabilize polylysine helix or polyarginine helix, for example, the pH should be more than the pK value. So you have to keep pH more than 10.6 in order to stabilize a polylysine helix. Or if you have, say, arginine helix, arginine side chain has pK value of 12.5, so you have to keep pH more than 12.5 so that polyarginine helix can be stable in solution.